Hello everyone, it's October 25th. Alright, let's do this. Height of binary tree after subtree removal queries. You're given the root of a binary tree with n nodes. Each node is assigned a unique value from 1 to n. You're also given an array queries of size m. You have to perform m independent queries on the tree, where the ith query, you do the following. Remove the subtree rooted at the node with the value queries I from the tree. Remove the subtree rooted at the node with a value. It is guaranteed that queries I will not be equal to the value of the root. Return an array answer of size m, where answer I is the height of the tree after performing the ith query. The queries are independent, so the tree returns to its initial state after each query. The height of the tree is the number of edges in the longest simple path. Okay, so for example, query 4, so remove 4, so the answer is 2. Longest single path. Okay, so first remove 3. It doesn't affect, so still gonna be 1, 2, 3. Remove 2. It's affect, so that will be 2. Remove 4. Still 3. And then remove 8. 2. Ooh. Basically, you say remove, you just don't count, right? I mean, if we pre-process the tree, we can know at each node what is the height of each node. Okay? What is the height of each node? And I also, okay, so at 5, so 5, 8, 9, 2, 1, 4, 6, 3, and 7. And if I know at this level 1, 2, 3, right? That's 3. This will be 2, right? This will be 1. And this will be 0, 0. This is 0, this is 1, and 0, and 0. If I know this, and I say I am going to remove 3, how do I know that it has no impact? Right, that's basically what we want to know. If you remove a tree, a subtree, does it have an impact? How do I know if it does not have impact? Well, we can probably get if it will be in the path. In the path. Yeah. If it's in the path of the locus. So if I go from here, eventually I go to the end. Ooh, go to the end. It's fine. Like here, I check yeah, I will not know which route, which can be on a path. But if I do it once and then do it once. So in here as 5, right? So I check the left is 2, right is 1. So I'll set, okay, so this one must be part of the thing. But I cannot propagate, right? I cannot propagate. Okay, so let's how about this? We run it once to get all the levels. Okay, we get all the heights, right? We get all the heights, and then we query it again. Okay, we query it again. So from each one, I check which one's bigger. So this one's bigger. So yeah, so we put this one here. So I go here, and here I check which one's bigger because you always follow the big one. So this one's bigger, so you go here, and this one we check which one's bigger. It's the same, so we go both. Okay. So now you have marked the nodes that has an impact on the height. Okay. Which means if the node that gets removed is not the one that gets marked, then it will not get impacted. So in this case it's 8, 2, 4, 6, right? So 8, 2, 4, these three are all impacted, right? The not really impacted, it has the potential of getting impacted, but 3 is not impacted, so I can immediately return the top, right? Okay, so now I say 2. 2, I need to remove 2, right? So when I remove 2, so this subtree is gone, right? And it's getting impacted. So yeah, this part of the tree does not exist. Which means I can do a parent, so I know who the parent is. So from parent, I can check left and right, so I know for me what my value is. So yeah. So it's if it's not impacted, it's just not impacted. But if it's the difficult part is if it's impacted, right? So if it's impacted, I know how much less out. So originally I contribute 2, right, in this path, but now I only contribute 1. I contribute 1, but then I can go up to my parent. Okay, I go up to my parent. So at this point, I remove, I go to my parent, I get my new weight, and I go to my parent, and then I go to my parent. Maybe because I'm just going to my parent, so that's log n, right? Maybe O and log n. You thought about that? So it doesn't matter which one I get 3, right? And when I remove, so I go to my parent, so this side is 0, the other side is 1, because this one, yeah, this the other side is 0. right? The other side is a 0. But how do I for each, because it's binary tree, right? It's binary tree. Yeah, it's binary tree, so you have 2. Right? You have 2 the length. So yeah, so this one I can get is 1, and then I find its parent because I updated it. I updated it. You don't update, you just go through, you have the current value. So we can create something like an array of array, right? An array, so each one will have 2 values. Yeah, number knows n, so we create an array of n, and the value is from 1, so okay, n plus 1, right? So for each one, we're gonna be like this. So each one will save its left child's height, right child's height. Okay. Oh, 3 things, and your parent. So each will store 3 things: left child, right child, and parent. And when I need to remove something, I go to that one. Okay. Find its parent. Now we find its parent. So from the parent side, parent can see the left and right, but parent doesn't know who is the left and who is the right. Parent does not know. But it does not matter. Parent doesn't need to know, right? So what parent knows is, parent does need to know. Well, no, it doesn't matter, because for me, right, hey, do I even know my height? Lord, we still need 4. Or maybe we can do a mapping. We do 2. 1 is just height. Okay. 1 is just height. Right? One is just heights. And the other we call it mapping, which each one just will have the left node and the right node and the parent. These are just node. Right node, left node, and parent. And then when I need to remove something, okay, I go to its parent, and the parent, I know the left, so current getting removed, so I go to the parent. So from parent, I check left, I check right, and then I find out their heights, right? And then because one of them gets removed, so that height is gone. It'll be good if we can update this, but the thing is, it's not necessary, right? It's not necessary. So I have the current node, so I go to the parent, right? And then from the parent, I have left and right. I got the one that's not been deleted, I got this. And I got the one that gets deleted, I got 0. So now I have this height. Then we just repeat, right? I got this height. I got repeat to the top, and I have, okay, let's try this. Let's give this a shot. Okay, so oh, I don't need this. So what we need is a DFS to produce the heights. Okay, so we need, oh, we don't even know the size. Jeez, man. They didn't give me n. And we can use map. I want to do like in one shot I got everything, but I think it's not possible. So I'll just use 2 hash map then. Because then we go one way, now we can handle everybody. Okay? Hash map. Alright, so I need to do 2 hash maps. So we can say a map of integer, right, and integer. We call this just heights. Alright. And we do another map, integer, with the int. We call it mapping. So we'll have node map to left, right, and parent. Okay, this is kind of what we want to do. And we'll say private void. Actually, no, not void. And this should be int. Get height. So given a tree node, we'll get its height, right? And we have to do a integer heights map integer int mapping. Okay. All right. So we have a node, and we have, if node is null, I just return 0. The height shall be 0. Actually, no. The height should be -1 because I go, actually no. Okay, so let's do the, it's not gonna be null. Okay, let's just say it's not gonna be null, because if it's null, because I need to find the maximum and then I need to +1. So yeah. Okay, let's not do this. So node, I'll go to the left. Right, I'll go to the right. So we say if node.left is not equal to null, okay, then we say left LH is 0, right H is 0, right? So if left is not null, then LH shall equal to get height node.left. Yep. Right, so that's getting the left height, and I don't think I need this. if node.right is not equal to null, then right h equal to get height node.right. Okay, so we get the left height, we get the right height. Now is my height. Now my height is going to be the maximum of the two, right? Now we just say heights dot put node dot value math dot maximum height of left and right. Oh, this is actually, you need to +1 because I have to which is +1, right? And we just maximum of the two. And mapping dot put node dot val. We're gonna say new int. Who's your parents? Okay, so left. So I say left node -1. Right node is -1. Actually, no, 0. 0 is 5. 0 is 5. So do 0, right? And yeah, okay. So we do this. Left node shall equal to node.left.val. Okay. And we do exactly the same thing here. We say right node equal to node.right.val. Okay. So once we're done, this is gonna be left node, right node, and parent.val. And once we're done, parent, I need to pass parent here. Dot left node, right? Node. And once we're done, we need to return in height. So we return heights dot get node dot val. That's my current height. All right, so I will run this. I call it get height root parents is null. We should do that. Parents is null. Actually no. Actually no. We can just do a new tree node. 0, right? Parents, because that's all I need about a parent. And then heights and mapping. Okay, so now we got a heights, now we got a mapping. Then we just go through each query, and then from the query we go to the top and then try to figure out what yeah, so we say okay, for int res equal to new int queries dot length. Okay, and then for int queue of queries. All right, so what we need to do is we go to queue, right, and then we find its parent, and then we get the parent's height, and now we do it again, and the parents become, right, and then we just keep going up until we go to the top. So we need to say for each queue we have its, let's say, current height. Okay, current height shall be heights dot get queue. That's the current height, and this height gets removed. Actually, that's not true because current height becomes 0, right? Because queue got removed, a height becomes 0, and we need to get its parent, right? Its parent shall equal to mapping dot get queue 0, 1, 2. Okay, this is the parent. Okay, we get its parent, and then we need to update its parent's current height, right? Which I feel like this one should go on the outside. Hold on, no. So we have child and a parent, right? And then we say, well, the parent is not. Okay, so you can say int child in C is equal to Q, and int P is equal to this. Okay, child parent. We say while parent is not equal to root val. Right, so we haven't hit that. We need to update parent's height. Child height, right? So for the parent, I can go to parent, so I have the left child and right child. So we can say the other child's height. Okay, other child's height. So int other height shall equal to we say mapping dot get current parent left child. The left child is equal to child. Okay, if left child is equal to child, then the other height should be the other child. So that shall be heights dot get mapping dot get p1, right? Otherwise, if the left is not, then we get the left. So heights dot get mapping dot get p0. Current child height. This is other child height. Okay, so now get the other child height. We get the other child height. So the current child height, and well, current child height actually is not 0 because we have also the 1, right? Because I have a child. Oh no, it is 0 because it's just got removed, right? It got removed. It is 0. So now we can say we just update, right? So we can say current child height shall equal to math the maximum current child height and other child height, right? So we update, basically it's just the parent height, right? We update the parent height, but we just assign it to child height, and we need to get its parent. Then we can say parent shall equal to mapping dot get p2, because parent's parent, right? So we get the current height, child height updated, and then we find its parent. So we'll go back up. Try it again. Go back up. Every time we go back up, every time we will. Oh, we have update C. So P is equal to. Oh, okay. Hold on. So C is equal to P. Right. So the next child is P, and the next parent is P's parent. And now we go into the last one when P is equal to root. And we actually should get P equal to root, right? Because if we jump out when P is not equal, when P is equal to root, yeah, I think shall be larger than 0, because I set the dummy parent as 0. So once the parent is larger than 0, then we keep going, right? And then when p is equal to 0, then we get out. So when we get out, we'll have ch child is this, p basically is 0. So the ch, the current child height, is the answer. So when we get out, we say res I shall equal to ch. Oh. So I0, I smaller than queries dot length, I plus plus. This can be queries I. This is also, and we can do C. Alright, current child height, child, parent. Other child height, so this is update current. Yeah, we don't have to write everything. So we do this now, and at the end I will return res. Okay, let's give this a try. So I have some confidence that this will, I think this is correct. The difficult part is I'm not sure if it's efficient enough. So basically we use, we keep track of each node's height and its left child, right child, and parent. We store this information in 2 hash maps. Then each time when a node is removed, we update, right? We update its parent's new height, and then move 1 level up to update its parent's height, so on and so forth, until we obtain the updated height of the root, right? I think it's on to get height, and we have on ok log n, right? So where n is the number of nodes in the tree, and k equal to the length of queries. All right, let's give this a shot. Let's hope it works. It'll be big if it works. It's like kind of like one shot we got this. All right, let's just run one. Let's see if it works. And the first it does not work. Well, it does not work because I think I used the wrong thing. Ooh, I got 1. There's a child height, and then we got a parent, right? So we are removing 4. So height of 3 is 1. Height of 1 is 2. I'm basically recalculating. Okay, hold on. So other height, I get it. Then we'll update because I have a child height, and then yeah, so it should be other height plus 1, because this one we do not remove. Child height removed, other one do not remove. And yeah, but then I got a new child height. So this shall be this height plus 1. I think it shall be plus 1 because this is the other one, right? And then we compare the two. Compare the current height, because the left height becomes 0, so current height and then the other height So we get a new height, right? So ch is the new height. Yeah, ch is the new height of basically the current parent. I got a new height, right? I got a new height. And then we go to parent, and then parent will say other height, and this height. So I do think if we keep it consistent, right, this is just height, and and because otherwise it's going to be 0. That's what we put in. Like it's just going to be 0. Hold on, let me think again. At each point I have the height. Okay, at each one I have the height. And if I go to my parent, okay, and I have this height, and since I go to my parent, I can add 1 because we have that. And parent will try to get to the other side. Right, we'll try to get to the other side. Yeah, there's some logic here. We'll get the other side as the height. So I think the height shall be -1. I think will make a lot of things easier to deal with. Like if it's a null, then just gonna be -1. Hold on, let me think again. Because you want to add 1. Actually, I don't want to add 1. Yeah, so because right now it's 0. Because the left height, right height, I just set it to 0, right? And I basically says if it's not equal to null, then we will. If it's equal to null, we set it to -1. Then at +1, that becomes 0, right? Yeah, think about it. Think about the implication if we just do, we do this. We say if node is equal to null, right? And we just return -1. Think about that. And then that will be 0. And then this is, yeah, so basically I was thinking, so we don't do the check here, right? So we do both here. So this will be fine. And this is equal to null, right? If it's equal to null, we do 0. Otherwise, node.left dot this. And we'll do exactly the same here. Equal to null. If it is 0, otherwise node dot val, not dot right dot val. Okay. And then right, and now it's the height. It's already at 1. And now we got the current height, we got this. Okay, so this is good. And then here is the same. Well, it's parent. Yeah, it's parent. Parent can be 0. Right? Parent can be 0. Okay. And we got a current child height. That should be -1 because I removed it. Right? Current child has -1. And I get a child, whatever the child is, I get a parent. And now all of this is fine. Other height, okay? Other height is going to be its height, right? Its height. And current height shall be the maximum of these two plus 1, right? That's the current height, is the maximum of these two plus 1. Because in that case, the height, because I have a left child and a right child. It depends, because the child can be 0, right? The child can be 0. So if I remove it and I try to get the other one, if it's a 0, oh, I just map it to -1, right? -1. I never have to. Hold on, I can do this. Height stop put 0. We put its height is -1. If we put that away, 0 is -1. We still have to. So we get height, we go to the left, right? Okay, so now height's 0 to -1, so this will become -1 if it doesn't have. Then it will be, -1, and if this is -1, that'll be negative, so there will be 0, right? And then we'll go up. Okay, let's give this a shot. So I think iron out a few. Okay, that's good. Let's run both. Okay, that's good. So let's give it a shot. Oh, I think we got timeout. So we can't just keep going through this. 37 or 40. So it's correct, but it's timeout. Okay, I mean, I have the other idea of doing this. So as long as it's not on the path, so we should be good. We can do that, right? We can do that. We can do a set. Put all the things that could be on the path as a star. So as we go through, if it's not in the path that can lead to the height of the root, that's not impacting, then we can return the answer immediately. We don't have to go through this. But if it's in here, then we have to go through this. Okay, so we can try this. Can we try this? So we go through this, right? How do we know which one is impacting? Well, we do know because I can go through the root. I know what the value is. I check its left, check its right. I see which one is bigger, right? If one is bigger, I choose it. If it's the same, I go both. So by doing this, we will be able to get a hash set. And then, but will this give us enough time? I don't know, honestly. I do not know. Do not know very well. Because it could be everything is on this. So we need a little bit better, right? We need a little better than that. And especially if we have this situation, we have 2, which means you remove 1, it doesn't matter, right? Like this. Yeah, I need to think about this. Okay, I think I'm gonna just close it for today because it's kind of late. I'll think about it. Hopefully I'll come up with some better idea. I feel like there's some caching that we can do. Like, I mean, keeping this in check, that's kind of a caching, right? So like if it's impacting, if it's not impacting, so we don't do it again. But what if it happens here? Like if I do 4, right? We shall be smart enough to say like, it's impacting, but it's duplicated, right? It's duplicated because both it and its and its sibling both are impacted. How do we how do we say something like that, right? How do we say something like that? So we know that if it's a 4, it's fine, like it's not really impacting, right? That's not really impacting. So the impacting, oh, you gotta be kidding me. Okay, so it can be a map. We do a map again. Technically no. Technically no. If I get, yeah, I don't need a map actually. If I go through this get height, and I do need a map to keep track of the relationships, the mapping. But after I've done this, I will obtain n, and then I can do heights as an array, right? Because I need to go through this again. I can populate the heights, and each time that someone has both children, yeah, it's kind of like you have redundancy. So I can do redundancy table, right? Redundancy table, and I just check its redundancy. If its redundancy is 1, redundancy, yeah, it's redundancy. So it means you move it, you remove it, you likely have changes. Like these redundancy is 2, and these redundancy is -1, right? Which means it does not impact. It does not impact. When it is 0, it does not impact. If it's 0, we just don't do anything. That's actually a good idea. Okay, so we can avoid a lot of computation. So finally, if it is impacting, okay, if it is impact, and that's the thing is, if we have like 2 branches, yeah, the redundancy need to be accumulated, because if this is good and all of these levels, right? So if I say this have a redundancy of 1, and then I come here, what redundancy is 1, right? And then, yeah, redundancy is 1. This redundancy is 2, right? This redundancy, because this redundancy is 1, and I go here, and then both are equal. So this redundancy become 2. This redundancy become 2, and then I come here. If this is one side and this side is bad, but this side's redundancy is also 2, right? It's not become 1. It's redundancy. We follow its parent. It has 2 redundancy as well. So if it got hit, it got more than 1 redundancy, that's fine, because I remove this, I have on the other side. It's good. So, but if these 2 are also the same, then its redundancy becomes 4. I mean, it's not really redundancy. It's just, at this point, does remove it cause a change, right? Does remove it cause a change? If it causes a change, I'll say let's set it to 1, right? If it will cause a change. If it does not cause a change, I'll set it to 0. And then I have these 2, because each time you only remove 1, right? So I have these 2. They're siblings, and remove one of them does not cause a change, right? They're siblings, remove 1. So that should set to 0. That's a false. Error does not cause a change. right? This is a false, this is false. And then we go to their children, right? Their children. And then remove their children also does not. So we should follow this. So whenever we have a false, yeah, we just have the redundancy, right? If these two have more children down, right? More children down, and even if these two children are supposed to be mapped, right? These are supposed to be mapped, and it's fine, right? This one is mapped, this one is mapped. But since we have redundancy, so if I remove this, it doesn't matter, right? It doesn't matter. So this, I say it's false. It's not impacting. This one's also not impacting. And this shall carry. It carries down to its children. This one carries down to its children as well. And all the children's. So basically, if we find a non-impact, then we don't have to go down. We don't have to, none of, like no matter how it changes down, none of them will be impacting. Because we always have redundancy. That's actually a good idea. That's actually a very good idea. That we only have a few that's impacting, right? And we'll try this first. And okay, yeah, we'll try it tomorrow. I'm now looking at a solution. I think we can solve this, and we still have time tomorrow. All right, I'll probably do another recording tomorrow.